Close your eyes and imagine the silence between heartbeats. In that tender pause, your body rests. Your mind grows still. And in this quietness, something magnificent awaits your attention. Tonight, you will discover one of the universe's most beautiful secrets. It lives in the smallest corners of reality. It whispers in the spaces between atoms. It dances in the quantum realm where ordinary rules dissolve like morning mist. This secret has a name. Scientists call it quantum entanglement. But names can never capture the full wonder of what it truly is. Picture two dancers on a stage so vast you cannot see its edges. These dancers move with perfect harmony. When one spins left, the other spins right. When one leaps, the other lands. They mirror each other with impossible precision. Now imagine something even more remarkable. Imagine these dancers are separated by millions of miles. One performs on Earth. The other dances on a distant star. Yet still, they move as one. Still, they share each step. Still, they dance in perfect unity. This is quantum entanglement. A connection so deep that distance becomes meaningless. A bond so strong that nothing in our everyday world can break it. You might wonder how this is possible. Your logical mind searches for invisible strings. It looks for hidden signals racing between the dancers. It seeks some explanation that fits the world you know. But there are no strings. There are no signals. There is only connection itself. Pure. Immediate. Unexplainable by the rules of our larger world. In the quantum realm, particles are born in pairs. They emerge from moments of pure energy. Like twins sharing the same heartbeat in their mother's womb, these particles share something deeper than space and time. Scientists create these quantum twins in laboratories. They split single particles of light called photons. The splitting happens in special crystals that act like cosmic midwives. One photon becomes two. One becomes many. Yet all carry the memory of their shared beginning. These newborn particles carry a secret code. It lives written in their quantum properties. Properties like spin, which you can imagine as the direction a particle faces. Up or down. Left or right. Clockwise or counterclockwise. But here's where the magic begins. Before anyone measures them, these particles exist in all possible states at once. They spin up and down simultaneously. They face all directions. They live in a dream state of infinite possibility. The moment someone observes one particle, everything changes. The act of measurement forces the particle to choose. It must decide, up or down, left or right. The quantum dream collapses into a single reality. And here comes the miracle. At that exact instant, no matter how far away, its entangled partner also chooses. Not randomly. Not by coincidence. But in perfect correlation with its twin. If the first particle chooses to spin up, the second instantly spins down. If the first turns left, the second turns right. They remain connected across any distance. They dance their eternal dance of perfect balance. Einstein himself struggled with this idea. He called it spooky action at a distance. The great genius who explained space and time found himself puzzled by this quantum mystery. He believed something must be traveling between the particles. Some hidden signal must carry the message. For decades, scientists wondered if Einstein was right. They designed clever experiments to test whether invisible messages raced between entangled particles. They looked for signals traveling at the speed of light. They searched for hidden pathways through space. What they found changed everything. No signals exist. No messages travel. The connection is immediate. Instantaneous. It happens faster than light itself could journey between the particles. This discovery shook the foundations of physics. It revealed a universe far stranger and more connected than anyone had imagined. A universe where separation is, in some deep sense, an illusion. Think about the atoms in your body right now. They came from ancient stars that died billions of years ago. Those stellar furnaces forged the calcium in your bones, the iron in your blood, the oxygen you breathe. Some of those atoms may once have been entangled with particles now scattered across the galaxy. The quantum connections may have faded over time, but the memory remains. You carry within yourself the echo of cosmic connections that span the universe. As you lie here tonight, your body is part of this vast web of quantum relationships. Every particle that makes you has a history of connection. Every atom has danced with others in the quantum ballet that shapes reality. Scientists are only beginning to understand what this means. They're learning to use entanglement to build quantum computers. These machines will solve problems that would take ordinary computers longer than the age of the universe. They're discovering that entanglement might help us communicate in ways that are perfectly secure. Messages that cannot be intercepted or decoded by anyone except the intended receiver. They're finding evidence that entanglement plays a role in how birds navigate during migration, how plants harvest sunlight so efficiently, how your own consciousness might emerge from quantum processes in your brain. But perhaps the most beautiful discovery is this: we live in a universe that is fundamentally connected. At the deepest level of reality, separation is an illusion created by our limited senses. The invisible threads that connect entangled particles remind us that nothing exists in isolation. Everything is part of a greater whole. Every part influences every other part in ways we're only beginning to understand. As sleep begins to call to you, let this thought settle into your awareness. You are not separate from the cosmos around you. You are woven into its fabric, connected to its dance, part of its eternal story. Tomorrow, the sun will rise on a universe where particles continue their quantum dance, where invisible threads stretch across impossible distances, where connection transcends all boundaries. But tonight, as your consciousness prepares to drift into dreams, you might wonder about the scientist who first felt troubled by this quantum strangeness. Picture a man walking alone through the streets of Princeton. His wild hair catches the morning breeze. His eyes hold the weight of cosmic questions. This is Albert Einstein in 1935, and something is troubling his brilliant mind. Einstein has already given the world his greatest gifts. He has shown us that time can stretch and bend. He has revealed that space itself can curve like a gentle hill. He has unlocked the secret that matter and energy are one. But now, quantum mechanics whispers something that makes him deeply uncomfortable. It suggests that particles can instantly affect each other across vast distances. No signal travels between them. No force carries the message. The connection simply exists. Einstein cannot accept this. His entire understanding of the universe rests on a simple, beautiful principle. Nothing can travel faster than light. Information needs time to journey from one place to another. The universe must make sense according to local rules. He sits at his desk, pen in hand, and writes a paper that will challenge quantum theory for decades to come. He calls the instant connection between particles a spooky action at a distance. The phrase carries his unease, his sense that something is terribly wrong with this picture. Einstein believes in what scientists call local realism. This means that objects only influence other objects near them. A ball can only be pushed by a hand that touches it. A wave can only move outward from its source. Cause and effect need time and space to work their magic. But quantum entanglement seems to violate this sacred rule. It suggests that measuring one particle instantly determines what happens to its partner, no matter how far away. The connection transcends space and time. To Einstein, this feels like madness. He imagines two magical coins that always land on opposite sides. Flip one in New York, and it shows heads. At that exact moment, its partner in Tokyo shows tails. No signal passes between them. No time elapses. The correlation is perfect and immediate. Einstein argues that this cannot be how reality works. He proposes that the particles must carry hidden information from the moment they are created. Like identical twins who secretly agree to always disagree, the particles must have predetermined fates. He calls these hidden instructions local hidden variables. They would be like invisible scripts that tell each particle exactly how to behave when measured. The particles would only appear to communicate instantly. In truth, they would simply be following their predetermined roles. This idea brings Einstein comfort. It preserves his vision of a universe where everything happens for local, understandable reasons. Where mystery gives way to elegant mathematical laws. Where God, as Einstein famously says, does not play dice with the universe. But the quantum physicists who work with Einstein see things differently. Niels Bohr, the gentle Danish scientist who helped birth quantum theory, argues with Einstein for hours. Their debates become legendary in the physics community. Bohr believes that quantum mechanics reveals something profound about reality itself. At the smallest scales, the universe genuinely operates by different rules. Particles really do exist in multiple states until observed. Entangled particles really do share an instant connection that defies classical logic. The debate between Einstein and Bohr becomes more than a scientific disagreement. It becomes a question about the nature of reality itself. Is the universe fundamentally predictable and local, as Einstein believes? Or is it strange and interconnected in ways that challenge our everyday understanding? For years, the argument remains philosophical. Scientists can observe entangled particles and see their correlations. But they cannot definitively prove whether hidden variables exist or whether the quantum world truly operates by spooky rules. Einstein never lives to see his question answered. He dies in 1955, still believing that quantum mechanics must be incomplete. Still convinced that a deeper, more sensible theory waits to be discovered. Still troubled by the idea that particles can read each other's minds across impossible distances. But Einstein's discomfort serves science beautifully. His questions force other scientists to think more deeply about what quantum mechanics really means. His challenge pushes them to design better experiments. His skepticism becomes a gift to future generations of researchers. In the quiet of your bedroom tonight, you can almost feel Einstein's wonder and worry. Here was a man who spent his life seeking the elegant simplicity behind nature's complexity. Who found deep beauty in the mathematical laws that govern space and time. Yet quantum entanglement suggests that reality is far stranger than even Einstein dared imagine. It hints at a universe where connection transcends distance. Where observation creates reality. Where the very act of asking a question changes the answer. Einstein's struggle reminds us that even genius has limits. Even the greatest minds can feel overwhelmed by nature's mysteries. The universe continues to surprise us, to challenge our assumptions, to reveal new layers of wonder. As you rest here in the darkness, consider how Einstein's questions still echo through modern laboratories. Scientists continue to probe the quantum world, seeking to understand what connection really means. They design experiments that would have amazed Einstein. They discover new forms of quantum strangeness that stretch our imagination even further. The man who called entanglement spooky could never have imagined how right he was about its strangeness. How wrong he was about its reality. How beautiful his doubts would prove to be. Einstein's discomfort with instant connections opens a door to deeper questions. If particles can be born together and remain forever linked, what happens in that moment of quantum birth? How do two separate things become one entangled system? In laboratories around the world, scientists work to answer this question by creating quantum twins in controlled conditions, watching the precise moment when connection transcends separation. Deep inside a laboratory, something magical is about to happen. A scientist adjusts a laser, pointing its beam toward a crystal no larger than your fingernail. The crystal sits perfectly still on a metal table, waiting for the touch of light that will awaken its hidden powers. This crystal is special. Its atoms are arranged in a pattern that can work miracles. When light enters its crystalline heart, something extraordinary occurs. One photon becomes two. A single particle of light divides, creating twins that share a mysterious bond. You can imagine this moment like the splitting of a soap bubble. one perfect sphere touches a surface and becomes two smaller bubbles. But these quantum bubbles carry something far more precious than soap and air. They carry the secret of connection itself. The process has a scientific name: spontaneous parametric downconversion. But the name cannot capture the wonder of what actually happens. A high-energy photon meets the crystal's atoms and gives up its energy to create two children of light. These newborn photons share all the properties their parent once possessed. Think of it like a mother's heartbeat dividing to beat in two chests. The original rhythm continues in both children, but each carries only half the energy. What they lose in power, they gain in connection. They become quantum twins, forever linked by their shared beginning. The moment of creation happens faster than thought itself. In less than a billionth of a second, the crystal transforms one particle into two. But the speed of birth cannot erase the bond that forms. The twins emerge carrying identical quantum signatures, like matching birthmarks written in the language of light itself. Scientists call these newborn particles photon pairs. But you might think of them as quantum soulmates. They are born from the same moment of light. They share the same quantum memories. They carry within their wave functions the echo of their unified past. The crystal acts like a quantum midwife, helping to deliver these twins into existence. Its atoms provide the energy needed for the transformation. Its structure guides the process with atomic precision. Its transparency allows the newborn photons to escape and begin their journey through the world. As the twin photons leave the crystal, they travel in different directions. One might head toward a mirror on the left. The other might journey toward a detector on the right. Distance begins to separate their paths, but it cannot separate their quantum hearts. Each photon carries properties that scientists can measure. They have polarization, which you can think of as the direction their light waves wiggle. They might vibrate up and down, or left and right, or at angles in between. This polarization becomes their quantum fingerprint. But here lies the mystery that troubled Einstein. Before anyone measures them, the twin photons exist in what scientists call a superposition. They are polarized in all possible directions at once. Up and down. Left and right. Every angle simultaneously. This quantum dream state continues until someone decides to look. The act of measurement forces each photon to choose a specific polarization. But the choice is not random. The twins remain perfectly correlated, even as distance grows between them. If you measure one photon and find it polarized vertically, its twin will instantly polarize horizontally. If you discover diagonal polarization in one, the other immediately adopts the opposite diagonal. They maintain perfect balance, like dancers who never lose their rhythm no matter how far apart they spin. The correlation happens faster than light itself could travel between them. No signal carries the message. No force connects their positions. The bond exists in the quantum realm, where ordinary rules of space and time hold no power. Scientists can create millions of these photon pairs every second. Each crystal can birth an endless stream of quantum twins. Each pair carries the same mysterious connection. Each set of twins demonstrates the same impossible correlation. The creation process is so reliable that researchers build entire experiments around it. They separate the photon twins by miles, sending them through fiber optic cables to different cities. They store them in quantum memories. They use them to test the very foundations of reality itself. Some photon pairs are sent to space, traveling to satellites that orbit high above Earth. Others journey through underground tunnels, protected from interference. Still others dance through the air itself, riding invisible beams between mountaintop telescopes. No matter how far they travel, the connection persists. The quantum bond that formed in the crystal's heart continues to link them across any distance. They remain two parts of a single quantum system, forever sharing their entangled fate. You might wonder what this moment of birth feels like for the photons themselves. Do they experience the splitting? Do they sense their newfound connection? These questions touch the deepest mysteries of consciousness and quantum mechanics. We cannot know what, if anything, a photon experiences. But we can observe the effects of their entanglement. We can measure their correlations. We can verify that their bond transcends the classical world's limitations. The birth of entangled photons happens in laboratories around the world every day. Each creation adds to our understanding of quantum mechanics. Each pair of twins teaches us something new about the nature of reality itself. These quantum births are more than scientific curiosities. They are windows into the fundamental structure of existence. They show us that separation is, in some deep sense, an illusion. That connection can transcend space and time. That the universe operates by rules far more mysterious and beautiful than we once imagined. As you rest in the quiet darkness of your room, consider the photon pairs being born this very moment in laboratories across the globe. Each crystal splitting light into quantum twins. Each pair carrying the secret of instant connection. Each birth adding to the growing web of entanglement that surrounds us. The creation of these quantum souls reveals something profound about the nature of relationship itself. But how do scientists communicate with these mysterious particles? How do they coax information from beings of pure light without destroying the very connections they seek to understand? In the delicate dance between observer and observed, a new chapter of quantum mystery begins to unfold. In the deepest silence of your bedroom, no words pass between you and the darkness. Yet something profound is happening. Your breath speaks to your lungs. Your heart whispers to your blood. Your body carries on countless conversations without making a single sound. This is how entangled particles speak to each other. Without words. Without signals. Without any language that our everyday world would recognize. Picture two friends who have known each other for so long that they finish each other's sentences. They sit in comfortable silence, yet each knows exactly what the other is thinking. Their connection runs deeper than words could ever express. Entangled particles share an even more intimate bond. When one reveals its quantum state, the other instantly knows how to respond. Not because any message travels between them. Not because they share secret signals. But because they are, in some fundamental way, still one system expressing itself in two places. Scientists spend years learning to speak with these quantum particles. They build machines that can ask very specific questions. Questions like, what is your polarization, or which way are you spinning? The particles always answer, but never in words we could hear. Instead, they respond with their entire being. A photon might absorb itself into a detector, creating a tiny flash of light. An electron might flip its magnetic orientation, changing the way it interacts with nearby atoms. These physical responses become their voice in our world. But here lies the beautiful mystery. The moment you ask one entangled particle a question, its distant twin already knows the answer it must give. Not because it overheard your question. Not because news of the measurement traveled to reach it. But because the question itself changes the entire quantum system that both particles share. Think of it like touching the surface of a perfectly still pond. Your finger creates ripples that spread outward in all directions. But in the quantum world, the ripples travel with infinite speed. They reach every part of the pond at exactly the same instant. When scientists measure one particle's spin, they are touching the quantum pond. The measurement creates waves that instantly inform the entire entangled system. The distant particle responds not to a signal, but to the change in their shared quantum reality. This communication transcends our normal understanding of time. In our world, conversations require duration. Sound waves need time to travel from mouth to ear. Light needs time to journey from star to eye. Even our thoughts need time to flow from neuron to neuron. But quantum correlations happen in zero time. The moment one particle commits to a particular state, its partner commits to the corresponding state. The delay between question and answer approaches absolute zero, no matter how vast the distance between them. Einstein called this spooky because it seemed to violate a sacred principle of physics. Nothing should be able to influence distant events faster than light can travel. Yet entangled particles seem to do exactly that, sharing information across impossible distances in impossible time. Modern experiments have tested this quantum communication with stunning precision. Scientists separate entangled photons by hundreds of miles. They measure one particle and record exactly when its twin responds. The correlation appears to be truly instantaneous, limited only by the precision of their measuring devices. This instant connection has profound implications for how we understand reality itself. It suggests that the universe is far more interconnected than we ever imagined. That separation, at the deepest level, might be an illusion created by our limited perspective. Consider the conversations happening in your own body right now. Molecules in your brain communicate through chemical signals. Cells in your heart coordinate their rhythm through electrical impulses. Every part of you is constantly talking to every other part. But what if these biological conversations are built upon an even deeper foundation? What if the quantum particles that make up your atoms still remember connections formed billions of years ago in the hearts of dying stars? Scientists are beginning to explore these possibilities. They study whether quantum entanglement plays a role in photosynthesis, helping plants harvest sunlight with remarkable efficiency. They investigate whether bird navigation relies on quantum correlations in specialized proteins. They wonder whether consciousness itself emerges from quantum conversations in the brain. These questions push at the boundaries of what science can currently answer. But they point toward a universe where communication exists at levels we are only beginning to understand. Where connection transcends the classical boundaries of space and time. The language without words that entangled particles speak may be the most fundamental form of communication in existence. It requires no medium to carry it. No time to transmit it. No energy to sustain it. It simply exists as pure correlation, pure connection, pure relationship. As you drift deeper into the quiet of this night, imagine the quantum conversations happening all around you. Particles in the air sharing their entangled histories. Atoms in your body maintaining connections forged in cosmic furnaces. A universe speaking to itself in whispers too subtle for our senses to detect. This silent dialogue continues every moment, in every corner of existence. It connects the smallest particles to the largest structures. It binds the present moment to the quantum memories of the past. But how do scientists actually witness these quantum conversations? What tools allow them to eavesdrop on the whispered correlations between distant particles, and what happens when they try to catch these connections in the act? Step quietly into a quantum physics laboratory in the deep hours of night. The room glows softly with the light of computer screens and laser beams. Scientists move with the careful reverence of people who know they are touching the edge of mystery itself. Here, in this temple of precision, researchers attempt something that seems impossible. They try to measure things so delicate that the very act of looking changes what exists. They seek to capture the dance of particles that exist in multiple states at once. Imagine trying to photograph a soap bubble without popping it. Your camera's flash might be too bright. The air from your movement might be too strong. Even the gentlest touch destroys the very thing you hope to preserve. This is the daily challenge that quantum physicists face. They must observe particles without disturbing them. They must ask questions without changing the answers. They must measure the unmeasurable with tools built from the very matter they seek to understand. The instruments in these laboratories are marvels of human ingenuity. Detectors so sensitive they can register the arrival of a single photon. Lasers so pure their light contains only one perfect frequency. Mirrors so precise they reflect waves without adding even the smallest distortion. But even the most perfect instruments cannot escape a fundamental truth. The act of measurement is itself a physical interaction. To see a photon, a detector must absorb it. To measure an electron's position, you must bounce other particles off it. To ask any question of the quantum world, you must touch it with the classical world. This touching changes everything. Before measurement, an entangled particle exists in what scientists call superposition. It spins in all directions simultaneously. It travels along every possible path at once. It lives in a dream state of infinite possibility. The moment you try to measure it, this quantum dream collapses. The particle must choose up or down, left or right, here or there. The measurement forces it to become real in our classical sense, abandoning all the possibilities it once held. Think of it like trying to catch a butterfly that exists in all parts of a garden at once. The moment you place your net, the butterfly must choose where to be caught. All its other possible locations vanish instantly. Your gentle capture creates the very reality you observe. Scientists have learned to work with this strange limitation. They design experiments that ask the right questions in the right way. They measure large numbers of identical particles, building statistical pictures of quantum behavior. They learn to read the shadows that quantum reality casts into our world. Some of the most beautiful measurements happen with polarized light. Scientists create photons with specific orientations and send them through special filters. If a photon's polarization matches the filter's orientation, it passes through. If not, it gets absorbed. But before measurement, the photon's polarization exists in superposition. It points in all directions at once. The filter forces it to choose, creating the very property that the measurement reveals. The act of observation literally brings the photon's polarization into existence. This happens with entangled particles too. When you measure one twin's polarization, you force both particles to abandon their quantum dreams. They must choose complementary states that preserve their perfect correlation. Your measurement of one creates the reality of both. The speed of this creation astounds even the scientists who study it. The moment one particle commits to a state, its distant twin immediately knows what it must become. The collapse of superposition happens faster than light could travel between them. Researchers have tested this with experiments of breathtaking precision. They separate entangled photons by hundreds of miles. They measure them at exactly the same time using synchronized atomic clocks. They verify that the correlations appear instantly, limited only by the speed of their measuring devices. These measurements reveal something profound about the nature of reality itself. They suggest that properties like polarization and spin are not fixed features that particles carry with them. Instead, they are relationships that emerge from the interaction between quantum systems and measuring devices. Your own body participates in countless quantum measurements every moment. Light enters your eyes and interacts with molecules in your retina. The quantum states of these photons collapse into the classical signals that become your vision. You are constantly creating reality through the act of observation. But most of these quantum measurements happen without your awareness. Your cells measure the quantum states of molecules during chemical reactions. Your DNA interacts with radiation in ways that create or destroy quantum correlations. Your entire biological existence rests on a foundation of quantum measurements. Some scientists wonder whether consciousness itself emerges from quantum measurement processes in the brain. They propose that the collapse of quantum superpositions in neural microtubules might create the stream of awareness that you experience as thought and feeling. These ideas remain at the frontier of scientific understanding. But they point toward a universe where measurement, observation, and consciousness are intimately connected. Where the act of asking questions helps create the reality that provides answers. In quantum laboratories, scientists have become artists of measurement. They craft experiments with the delicacy of poets and the precision of mathematicians. They learn to ask questions that reveal truth without destroying the beauty they seek to understand. Each successful measurement is a small miracle. A moment when the quantum world allows itself to be glimpsed without completely vanishing. A brief window into realities that exist beyond our everyday experience. The instruments hum softly in the darkness, continuing their patient dialogue with particles too small to see. Detectors wait for the arrival of single photons. Computers analyze correlations that span continents. Scientists maintain their vigil at the border between the quantum and classical worlds. As you rest in the quiet of your room, countless quantum measurements are creating the reality around you. Light from distant stars collapses into definite states as it touches your walls. Thermal radiation from your body interacts with their molecules in ways that constantly remake the quantum environment. You are both observer and observed, measurer and measured, in the grand quantum experiment that is existence itself. But what happens when particles exist in multiple states simultaneously, like the famous cat that is both alive and dead? How do we understand this strange quantum twilight where contradictions become comfortable companions? In a thought experiment that has puzzled minds for nearly a century, a cat sits quietly in a sealed box. This is no ordinary cat, and this is no ordinary box. This is Schrödinger's cat, living in the strange twilight between existence and non-existence. The Austrian physicist Erwin Schrödinger created this imaginary scenario in 1935 to illustrate something that troubled him deeply about quantum mechanics. He wanted to show how the bizarre rules of the quantum world, when applied to everyday objects, lead to impossible situations. Inside the box with the cat sits a Geiger counter, a small amount of radioactive material, a hammer, and a flask of poison. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggers the hammer, breaks the flask, and releases the poison. The cat dies. But according to quantum mechanics, before anyone opens the box to look, the radioactive atom exists in superposition. It is both decayed and not decayed simultaneously. This means the cat must also exist in superposition. It is both alive and dead at the same time. This seems absurd to our everyday understanding. Cats are either alive or dead. There is no in-between state. Yet quantum mechanics insists that until observed, the entire system remains suspended in all possible states simultaneously. You can imagine this paradox as a story that exists in your mind before you choose how it ends. The characters live in a state of infinite possibility. They might fall in love or part forever. They might succeed or fail. All outcomes coexist until you decide which story to tell. Schrödinger's cat lives in this same state of infinite possibility. The box contains not one reality, but all possible realities laid upon each other like transparent dreams. The cat that purrs. The cat that sleeps eternal sleep. Both exist together in quantum superposition. This paradox reveals something profound about the role of observation in quantum mechanics. The act of opening the box and looking inside forces the system to choose. The superposition collapses. The cat becomes definitively alive or definitively dead. Reality crystallizes from the mist of possibility. But what exactly counts as observation? Does it require a conscious mind? Or would any interaction with the environment collapse the superposition? This question touches the deepest mysteries of quantum mechanics and consciousness itself. Some interpretations suggest that consciousness plays a special role in collapsing quantum states. The cat remains in superposition until a conscious observer opens the box and looks inside. At that moment, the observer's awareness somehow selects which reality becomes real. Other interpretations argue that any interaction with the environment acts as an observation. The air molecules in the box, the photons bouncing around, even the gravitational field of nearby objects could collapse the superposition. Consciousness is not required. The physical world observes itself. Still, other interpretations propose that all possible realities actually exist simultaneously in parallel universes. When you open the box, you don't collapse the superposition. Instead, you discover which branch of reality you happen to inhabit. In another universe, the cat met a different fate. These competing explanations show how quantum mechanics challenges our most basic assumptions about reality. Is there one objective truth that exists independent of observation? Or does reality emerge from the interaction between quantum systems and conscious minds? The paradox extends far beyond imaginary cats in boxes. Every quantum particle exists in superposition until measured. Every atom in your body lives in multiple states simultaneously until some interaction forces it to choose. Consider the air you breathe right now. Each molecule moves along countless possible paths. It vibrates in multiple energy states. It interacts with other molecules in all possible ways. Yet somehow, from this quantum chaos, emerges the ordered reality of your breath entering and leaving your lungs. Your eyes detect light that has traveled from distant stars. Each photon exists in superposition as it journeys through space. It might be absorbed by dust. It might scatter off gas clouds. It might reach your retina or miss it entirely. All possibilities coexist until the moment it interacts with molecules in your eye. Even your thoughts might emerge from quantum superpositions in your brain. Some scientists propose that consciousness arises when quantum states in neural microtubules collapse in orchestrated patterns. Your awareness might be the universe observing itself at the quantum level. This idea remains highly speculative, but it suggests a beautiful possibility. Perhaps consciousness and quantum mechanics are intimately connected. Perhaps your thoughts participate in the ongoing creation of reality through countless microscopic observations. The paradox of knowing and not knowing touches something fundamental about existence itself. We live in a universe where definite answers emerge from indefinite questions. Where certainty crystallizes from uncertainty. Where the act of seeking truth helps create the truth we find. As you rest in the darkness of your room, you exist in your own kind of superposition. You are neither fully awake nor fully asleep. Your consciousness hovers between different states of awareness. You experience the quantum-like transition between waking reality and dream reality. In this liminal space, the boundaries between possible and actual become soft. Your mind explores multiple thoughts simultaneously. Your imagination creates realities that exist only in the superposition of your awareness. You become both observer and observed in the theater of your own consciousness. Schrodinger's cat continues to wait patiently in its box, existing in all possible states until someone decides to look. The paradox it represents has no easy resolution. It points toward mysteries that may always remain at the edge of human understanding. But perhaps this uncertainty is not a flaw in our knowledge. Perhaps it reveals something beautiful about the nature of existence itself. Perhaps reality is not a fixed stage but an ongoing conversation between possibility and actuality. Somewhere in the quantum realm, particles continue to exist in superposition until they encounter the gift of measurement, and a physicist named Bell discovered a way to test whether this quantum strangeness could be proven real. In 1964, a quiet physicist named John Stuart Bell sat at his desk and changed the world forever. He was not trying to revolutionize science. He was simply trying to understand what Einstein had meant when he called quantum entanglement spooky action at a distance. Bell wondered if Einstein might be right. Perhaps particles only appeared to communicate instantly across vast distances. Perhaps they carried hidden instructions from the moment of their birth, like secret letters that told them exactly how to behave when measured. To test this idea, Bell created something extraordinary. He wrote down a mathematical inequality that could distinguish between two very different versions of reality. One where particles carried hidden information. Another where quantum entanglement was genuinely magical. This mathematical test became known as Bell's theorem. It sounds complex, but at its heart lies a simple and beautiful question: can any local theory explain the perfect correlations we observe between entangled particles? Imagine two coins that always land on opposite sides when flipped. If you flip one in New York and it shows heads, its partner in Tokyo will show tails. Every single time. No exceptions. Perfect correlation across any distance. Einstein believed these coins must have secret programming. Perhaps one coin always chooses heads while the other always chooses tails. Their behavior appears magical, but it follows predetermined rules written into their hidden properties. Bell's genius was realizing that hidden programming could only create correlations up to a certain mathematical limit. If particles carried secret instructions, their correlations could be strong, but not perfect. There would always be some statistical boundary they could not cross. But quantum mechanics predicted correlations that exceeded Bell's limit. It suggested that entangled particles could achieve perfect coordination that no hidden variable theory could explain. The mathematics pointed toward genuine magic in the fabric of reality. For years, Bell's theorem remained a beautiful piece of theoretical physics. Scientists admired its elegance, but technology was not yet advanced enough to perform the delicate experiments needed to test it. Then, in the 1970s and 1980s, researchers began building the instruments necessary to measure Bell's inequality in real laboratories. They created entangled photons and separated them by large distances. They measured their correlations with unprecedented precision. The results were stunning. Again and again, the experiment showed correlations that violated Bell's inequality. The particles achieved perfect coordination that exceeded the mathematical limits of any local hidden variable theory. These measurements proved something that seemed impossible. The universe really does contain connections that transcend space and time. Entangled particles really do share instantaneous correlations that cannot be explained by classical physics. Einstein's hidden variables were not there. The particles did not carry secret instructions. Their perfect correlations emerged from something far more mysterious than predetermined programming. They emerged from the quantum nature of reality itself. Bell's theorem opened a window into the deepest structure of existence. It showed that the universe is fundamentally non-local. That some relationships transcend the boundaries of space and time. That connection itself is woven into the fabric of reality at the most basic level. Think about what this means for your understanding of the world. Every day, you experience a reality that appears local. Objects only influence other objects when they touch. Causes take time to create effects. Information needs physical carriers to travel from place to place. But Bell's theorem reveals that this local appearance is an illusion created by our limited perspective. At the quantum level, the universe operates by different rules. Particles can share correlations that exist outside of space and time. Connection transcends distance in ways that challenge everything we thought we knew about reality. The violation of Bell's inequality became one of the most important discoveries in the history of science. It proved that quantum mechanics reveals something genuinely new about the nature of existence. Something that cannot be reduced to classical explanations or hidden mechanisms. Scientists continue to test Bell's theorem with ever greater precision. They close experimental loopholes that might allow local explanations to sneak back in. They separate entangled particles by thousands of miles. They use cosmic photons from distant quasars to choose measurement settings. Every test confirms the same remarkable conclusion. The universe really is non-local. Quantum entanglement really does create instantaneous correlations across any distance. The connections between particles transcend the classical boundaries of space and time. These discoveries have profound implications that extend far beyond physics laboratories. They suggest that separation itself might be an illusion. That everything in the universe might be connected at levels we are only beginning to understand. Consider the atoms that make up your body right now. They were forged in the hearts of ancient stars billions of years ago. Some of them might still carry quantum memories of their stellar origins. Some might still be entangled with particles scattered across the galaxy. Bell's theorem tells us that these connections, if they exist, would be real and immediate. They would not be weakened by distance or diminished by time. They would represent genuine bonds that link you to the cosmic history that created you. The mathematics that Bell created continues to inspire new discoveries. Scientists use variations of his theorem to explore quantum communication, quantum computing, and quantum cryptography. They find new ways to test the boundaries between classical and quantum reality. But perhaps the most beautiful aspect of Bell's work is how it transforms our relationship with mystery itself. It proves that the universe contains genuine magic. Not the magic of fairy tales and superstition, but the magic of deep mathematical truth that transcends ordinary understanding. As you rest in the quiet darkness, you can feel the weight of this discovery settling into your awareness. The universe is stranger and more wonderful than anyone had dared imagine. Connection exists at levels that defy classical explanation. Bell's theorem stands as a monument to human curiosity and scientific courage. It shows what becomes possible when brilliant minds refuse to accept easy answers. When they push past the boundaries of conventional thinking to discover new truths about reality. The mathematical poetry that Bell wrote in 1964 continues to echo through laboratories around the world. Each experiment confirms what his equations predicted. Each measurement adds another note to the growing symphony of evidence for quantum non-locality. But how do scientists actually use these quantum connections? Can entanglement serve practical purposes, or does it remain forever locked in the realm of pure mystery? The word teleportation conjures images from science fiction movies. Starship crews dissolving into sparkles of light. Heroes vanishing from one place and instantly appearing in another. Matter itself leaping across space in defiance of every physical law. Quantum teleportation is both more subtle and more profound than these fictional fantasies. No particle travels from point A to point B. No matter dissolves and reassembles elsewhere. Instead, something far more mysterious happens. Information itself transcends space. Imagine you have a favorite song written on a piece of paper. The melody, the rhythm, the emotions it evokes, all captured in musical notation. Now imagine that somehow, without moving the paper itself, you could perfectly recreate every note, every pause, every feeling of that song on another sheet of paper thousands of miles away. This is the essence of quantum teleportation. The quantum song that defines a particle's identity can be perfectly reproduced in a distant particle without any physical object making the journey between them. The process begins with three particles. Two of them are entangled twins, sharing the mysterious quantum connection that Bell's theorem proved was real. The third particle carries the quantum information that scientists want to teleport. Picture these particles as three dancers on a cosmic stage. Two dancers hold hands, their movements perfectly synchronized through their entangled bond. The third dancer carries a specific choreography, a unique pattern of quantum states that defines its identity. The goal is to teach this choreography to one of the entangled dancers without them ever meeting directly. To transfer the quantum information across space using only the mysterious connection between the entangled twins. The process unfolds like a carefully orchestrated ballet. First, scientists perform a special measurement that entangles the original particle with one of the quantum twins. This measurement destroys the original particle's quantum state, but it creates a new connection that links all three particles together. At the exact moment this measurement happens, the distant entangled twin spontaneously acquires the quantum choreography that the original particle once possessed. The information has teleported across space, riding on the invisible threads that connect entangled particles. But there's a beautiful catch. The receiving particle doesn't automatically know it has acquired new information. It exists in a quantum superposition of all possible states. Additional steps are needed to complete the teleportation process. The scientists who performed the original measurement obtain classical information about what they found. They must send this information through normal channels, perhaps a phone call, an email, or a radio signal. This classical message travels at the speed of light or slower. Only when the classical information arrives can the receiving particle be properly prepared. Scientists use this information to perform specific operations that reveal the teleported quantum state. The distant particle transforms, becoming an exact quantum copy of the original. This process preserves one of quantum mechanics' most fundamental principles. The original particle's quantum state is completely destroyed during the teleportation. You cannot make perfect copies of quantum information. You can only move it from one place to another. Think of it like transferring your consciousness into a new body. The process might preserve every memory, every thought pattern, every aspect of your identity. But the original you would cease to exist in the process. Identity travels, but it cannot be duplicated. Quantum teleportation has been achieved in laboratories around the world. Scientists have teleported photons across cities, through fiber optic cables, and even to orbiting satellites. They have teleported the quantum states of atoms, ions, and complex molecular systems. Each successful teleportation proves something remarkable about the nature of information itself. Quantum information is not bound to specific particles. It can exist as pure pattern, pure relationship, pure mathematical structure that transcends its physical substrate. This discovery opens possibilities that stretch the imagination. Quantum computers might use teleportation to move information between distant processors. Quantum networks might connect laboratories across continents through teleported data streams. Some scientists envision a future quantum internet where information travels through entangled connections rather than physical cables. Messages would arrive instantly at their destinations, protected by the fundamental laws of quantum mechanics from any attempt at interception. But quantum teleportation also raises profound questions about the nature of identity and existence. If a particle's essential properties can be perfectly recreated elsewhere while the original is destroyed, what does this tell us about what makes something real? Consider your own identity. What makes you you? Is it the specific atoms that comprise your body? Or is it the pattern of information, memories, thoughts, relationships, that gives meaning to those atoms? Your body replaces most of its atoms every few years. The calcium in your bones, the carbon in your muscles, even the neurons in your brain are constantly being renewed. Yet you maintain a continuous sense of self through all these changes. Perhaps your identity, like quantum information, exists as a pattern that transcends its physical substrate. Perhaps consciousness itself is something that could theoretically be teleported, moving from one biological system to another while preserving everything essential about who you are. These questions remain at the frontier of both science and philosophy. But quantum teleportation shows us that information can have an existence independent of the matter that carries it. That pattern and relationship might be more fundamental than substance and form. As you drift toward sleep tonight, your consciousness begins its own kind of teleportation. Your awareness shifts from the waking world into the realm of dreams. Your sense of self travels into landscapes that exist only in your imagination. This natural transition mirrors something profound about quantum teleportation. Identity is not fixed to place or time. It can move, transform, and exist in multiple states simultaneously. The boundaries between here and there, self and other, real and imaginary, become fluid and permeable. In your dreams, you might find yourself in distant places, living other lives, experiencing realities that transcend the physical limitations of your sleeping body. Perhaps this nightly journey offers a glimpse into the deeper truth that quantum teleportation reveals. But as quantum connections spread across laboratories and cities, scientists begin to wonder about an even grander possibility: could the entire universe be woven together by invisible threads of entanglement? Look up at the night sky from your window. Each pinprick of light represents a star that burned billions of years ago. Their ancient light has traveled unimaginable distances to reach your eyes tonight. But perhaps something deeper than light connects you to those distant suns. Scientists are beginning to discover that quantum entanglement might extend far beyond laboratory experiments. It might weave invisible threads throughout the entire cosmos. From the smallest subatomic particles to the largest galactic structures, everything might be connected by quantum correlations that transcend space and time. This cosmic web of connection begins in the very first moments after the Big Bang. In that primordial fireball, all matter and energy existed in a state of perfect unity. Every particle that would ever exist was compressed into a single point of infinite possibility. As the universe expanded and cooled, particles began to separate. But many retained quantum memories of their unified beginning. Photons that emerged from the cosmic microwave background still carry correlations that span the entire observable universe. Think of it like a vast symphony orchestra that was once seated in perfect harmony around a single conductor. When the performance begins, the musicians spread out across an enormous concert hall. Yet they continue to play in synchrony, their music coordinated by an invisible rhythm that transcends the distances between them. The atoms in your body carry their own cosmic symphony. They were forged in the nuclear furnaces of ancient stars. When those stars died in spectacular explosions, they scattered their atomic children across the galaxy. Some of those wandering atoms eventually found their way into the primordial cloud that became our solar system. Each atom in your blood, your bones, your breath, carries the quantum signature of its stellar birthplace. Some might still be entangled with particles that travel to distant corners of the universe. Others might maintain correlations with atoms in other people, other planets, other star systems. Consider the iron in your blood. It was created in the core of a massive star that died before our sun was born. During the star's final moments, iron atoms were scattered in all directions. Some became part of Earth. Others journey still through interstellar space. Yet quantum mechanics suggests they might all remain subtly connected. This connection operates through what scientists call quantum non-locality. It transcends the classical boundaries that seem to separate one place from another. It suggests that at the deepest level, the universe might be a single, interconnected quantum system expressing itself through countless individual parts. Galaxies themselves might be connected by quantum threads. The supermassive black holes at their centers could maintain entangled relationships that coordinate galactic evolution across cosmic time. Dark matter, which outweighs visible matter by 5 to 1, might serve as a quantum communication network that spans the universe. Some scientists propose that the large-scale structure of the cosmos, the way galaxies cluster into vast filaments and walls, might emerge from quantum correlations that existed in the earliest moments after the Big Bang. The universe might be shaped by invisible connections that operate faster than light. Even time itself might be woven from quantum entanglement. Some theories suggest that the flow of time emerges from the constant creation and destruction of quantum correlations throughout space. Past, present, and future might be different perspectives on a single, timeless quantum tapestry. These ideas push at the very limits of current scientific understanding. But they point toward a universe that is far more unified and interconnected than our everyday experience suggests. A cosmos where separation is an illusion created by our limited perception. Your consciousness might participate in this cosmic web of connection. The quantum processes in your brain could be entangled with quantum fields that permeate all of space. Your thoughts might ripple through the quantum vacuum, creating subtle influences that extend beyond your body. When you feel a sense of connection to nature, to other people, to the universe itself, you might be sensing something real at the quantum level. The mystical experience of unity that poets and philosophers have described for millennia might reflect an actual feature of physical reality. Scientists are developing new ways to test these cosmic connections. They study the quantum correlations in the cosmic microwave background radiation. They look for entanglement signatures in the light from distant quasars. They design experiments that could detect quantum non-locality on astronomical scales. Quantum telescopes might one day reveal the invisible threads that connect distant galaxies. Quantum sensors could map the entanglement structure of space-time itself. We might discover that the universe is far more like a living organism than a mechanical clockwork. These discoveries would transform our understanding of our place in the cosmos. Instead of being isolated specks of consciousness adrift in empty space, we would be recognized as integral parts of a vast, interconnected whole. Our thoughts, our actions, our very existence would be seen as expressions of cosmic-scale quantum processes. The air you breathe right now contains atoms that were once part of dinosaurs, ancient forests, and distant stars. But beyond this material connection, quantum entanglement suggests a deeper unity. Every breath might exchange not just matter and energy, but quantum information that links you to the entire history of the universe. Your heartbeat synchronizes with rhythms that began in the cosmic microwave background. Your neural activity resonates with quantum fields that connect every conscious being. Your dreams might access information stored in the quantum structure of space-time itself. As you prepare for sleep, you become part of the universe's nightly ritual of rest and renewal. Across the cosmos, stars are being born and dying. Galaxies are dancing their slow gravitational ballet. Black holes are processing information at the quantum level. All of these cosmic processes might be subtly connected to your own transition into sleep. Your consciousness might tap into quantum correlations that span the universe. Your dreams might access memories stored in the cosmic web of entanglement. The boundaries between self and cosmos, between mind and matter, between local and global, begin to dissolve. You are not separate from the universe. You are the universe experiencing itself subjectively through the lens of human consciousness. In this vast web of cosmic connection, every thought and feeling becomes significant. Every moment of awareness contributes to the ongoing evolution of universal consciousness. But could this cosmic web of connection extend beyond the physical universe? Could quantum entanglement carry something as precious and mysterious as love itself across the infinite distances between hearts? In the quiet moments before sleep, your thoughts often drift to people you love. Even when they are far away, you feel their presence somehow. Their influence on your heart seems immediate, unbound by distance or time. This feeling is so universal that every culture has words for the invisible threads that connect loving hearts. Science tells us that quantum entanglement cannot carry messages. It cannot transmit emotions across space. Yet the correlation it creates between particles mirrors something profound about human connection. The instant response of entangled twins echoes the way loving hearts seem to resonate across any distance. Consider what happens when someone you love is in distress. Sometimes you feel their pain before any news arrives. Sometimes you wake in the night with an inexplicable urge to call them, only to discover they needed you at that exact moment. These experiences feel real and immediate, even when rational explanation seems impossible. Perhaps these moments of connection operate through mechanisms we do not yet understand. Perhaps human consciousness, which emerges from quantum processes in the brain, can create correlations that transcend the physical boundaries of individual bodies. The molecules in your body were once part of other people. The carbon in your cells might have been part of someone's breath centuries ago. The water in your blood might have fallen as rain on ancestors you never met. At the material level, all human beings share a common molecular heritage. But quantum mechanics suggests an even deeper sharing. The particles that make up your atoms might still carry quantum memories of their previous relationships. They might remain subtly correlated with particles in other people, creating an invisible web of connection that spans all of humanity. When you love someone deeply, you share more than emotions and experiences. You share physical space, breathing the same air, touching the same objects. Your quantum fields intermingle in ways too subtle for current science to measure. Perhaps love creates quantum entanglements between conscious beings. This idea remains purely speculative. No experiment has yet detected quantum correlations between human brains. No measurement has captured the entanglement of hearts across distance. Science cannot prove that love travels faster than light. Yet the question itself illuminates something beautiful about both quantum mechanics and human experience. Both reveal that connection transcends our ordinary understanding of space and time. Both suggest that separation is, in some fundamental sense, an illusion. Think about the people who have shaped your life most profoundly. Their influence continues even when they are absent. Their words echo in your thoughts. Their love influences your choices. Their presence lives within you in ways that distance cannot diminish. This persistent influence resembles the way entangled particles maintain their correlation across vast distances. The connection created by shared experience, like the connection created by shared quantum birth, seems to exist outside the normal rules of space and time. Neuroscience reveals that loving relationships actually change the structure of your brain. The neural pathways formed through deep connection remain active throughout your life. Your brain carries physical traces of every person you have loved, every moment of genuine connection you have experienced. These neural traces might create quantum correlations that extend beyond your individual consciousness. When you think of someone you love, quantum processes in your brain might resonate with quantum processes in theirs. The thought of connection might create the reality of connection. Mirror neurons in your brain fire when you observe someone else's actions, as if you were performing those actions yourself. This neural mirroring happens automatically, creating a kind of physical empathy that transcends the boundaries of individual bodies. Perhaps this mirroring extends to the quantum level. Perhaps conscious beings can share quantum states in ways that create genuine correlation across distance. Perhaps love is the subjective experience of quantum entanglement between minds. These possibilities push at the edge of current scientific understanding. They venture into territory where physics meets consciousness, where measurable phenomena encounter unmeasurable experience. They ask whether the universe contains room for connections that transcend physical explanation. Even if love cannot travel faster than light in any literal sense, it operates by principles that quantum mechanics has made familiar. It creates correlations that seem to transcend space and time. It generates responses that appear instantaneous. It connects separate beings in ways that classical physics cannot fully explain. The laboratory of your heart conducts experiments that no scientific instrument can duplicate. It tests the boundaries between self and other. It explores the connections that make consciousness possible. It investigates the correlations that give meaning to existence. As you rest in the darkness tonight, you can feel the presence of everyone you have ever loved. They exist not just in your memory but in the quantum fabric of your being. Their influence ripples through your thoughts like waves through still water. Perhaps the atoms in your body still remember dancing with the atoms in theirs. Perhaps the quantum fields that surround you maintain subtle correlations with the quantum fields that surround them. Perhaps love creates a kind of entanglement that science has not yet learned to measure. The question of whether love travels faster than light may never find a definitive answer. But asking the question opens our minds to possibilities that transcend the boundaries between science and poetry, between physics and philosophy, between understanding and mystery. In the end, the connections that matter most may be the ones that cannot be measured or quantified. They exist in the space between hearts, in the quantum realm where correlation transcends causation, in the mysterious territory where consciousness meets the fundamental structure of reality. Love may not travel faster than light, but it illuminates truths that light itself cannot reveal. It shows us that connection is more fundamental than separation, that relationship is more basic than isolation, that the universe is held together by bonds stronger than gravity. Tonight, as consciousness prepares to dissolve into dreams, you join an eternal dance of connection that began with the first quantum correlation and continues in every moment of genuine love. Your breath grows slower now. Deeper. More peaceful. As sleep approaches, the boundaries between your conscious mind and the quantum world begin to soften. You become part of an ancient dance that has continued since the very beginning of time. In laboratories around the world, scientists continue their patient work. They create new pairs of entangled particles. They test the limits of quantum correlation. They push deeper into the mysteries that Einstein called spooky. But their experiments only reveal what has always been true: the universe is woven together by invisible threads of connection. The photons being born in crystals tonight will carry their quantum bonds across continents and centuries. Some will be separated by distances so vast that light would take years to travel between them. Yet their correlation will remain perfect, immediate, eternal. This is the dance that every particle in your body knows by heart. The carbon atoms in your cells were once locked in ancient limestone, part of sea creatures that lived millions of years ago. The iron in your blood was forged in the nuclear fire of a dying star. The oxygen you breathed was exhaled by countless plants and trees over billions of years. Each of these atoms carries quantum memories of its cosmic journey. Each one has been entangled with other particles countless times. Each one participates in the ongoing conversation between all matter in the universe. As you settle deeper into your pillow, you become conscious of this vast inheritance. Your body is not just flesh and bone. It is crystallized starlight. It is the universe experiencing itself through the lens of human awareness. The quantum field that surrounds you extends through your bedroom, through your house, through the entire planet. It connects you to every other conscious being. It links your dreams to the dreams of everyone who has ever lived or ever will live. In this field, time moves differently. Past and future become fluid concepts. The quantum correlations that formed in the first moments after the Big Bang still ripple through space. The entangled particles being created in tomorrow's experiments already exist in potential, waiting for their moment of birth. Your consciousness rides these quantum waves like a surfer riding swells in an infinite ocean. Each thought creates ripples that spread outward through the field. Each feeling generates correlations that connect you to the larger patterns of existence. Sleep itself becomes a form of quantum entanglement. As your awareness fades from the waking world, it becomes correlated with deeper states of being. Your individual consciousness merges with the collective unconscious that Jung described. Your personal dreams become part of humanity's shared dreaming. The neurons in your brain, firing in slower rhythms now, create quantum coherences that span your entire nervous system. Information flows through channels that classical physics cannot fully explain. Your mind accesses memories and insights that seem to come from beyond your individual experience. Perhaps in sleep, your consciousness touches the quantum vacuum itself. This invisible sea of energy that fills all of space contains the potential for every particle, every thought, every possibility. In dreams, you might swim in this ocean of pure potential. Ancient wisdom traditions have always spoken of the interconnectedness of all things. They described a cosmic consciousness that underlies individual awareness. They taught that separation is an illusion, that all beings are part of a single, unified whole. Quantum mechanics gives these mystical insights a scientific foundation. It shows that connection really does transcend space and time. It proves that correlation can exist without causation. It reveals that the universe operates more like a single mind than a collection of separate objects. As your breathing becomes even softer, you might sense this unity directly. The atoms in your body resonate with quantum fields that stretch across the galaxy. Your heartbeat synchronizes with rhythms that began in the cosmic microwave background. Your brainwaves align with patterns that connect all conscious beings. The entangled particles that scientists study in their laboratories are not exotic curiosities. They are windows into the fundamental nature of existence. They show us that everything is connected to everything else in ways that transcend our ordinary understanding. Your journey tonight through the quantum world of entanglement has revealed profound truths. You have learned that reality is far stranger and more beautiful than classical physics suggested. You have discovered that the universe operates by principles that seem almost magical. But perhaps the most important discovery is this: you are not separate from the cosmos you observe. You are part of it. Your consciousness emerges from quantum processes that connect you to every star, every planet, every living being. In the laboratory of sleep, your mind continues its quantum experiments. It explores states of being that exist beyond the boundaries of space and time. It participates in the ongoing creation of reality through observation and correlation. The dreams that come to you tonight will be woven from quantum threads that stretch across the universe. Your sleeping mind will dance with possibilities that exist in superposition until the moment of awakening collapses them into memory. Each dream becomes an experiment in consciousness. Each image that forms in your sleeping mind creates new correlations in the quantum field. Each story your brain tells becomes part of the larger story that the universe tells about itself. The particles in your body will continue their ancient dance while you sleep. They will maintain their quantum correlations with distant partners. They will participate in the ongoing conversation between all matter and energy in the cosmos. Tomorrow, you will wake to find the world unchanged yet somehow transformed by your journey through the quantum realm. The same objects will surround you, but you will see them with new eyes. You will understand that nothing exists in isolation, that everything is connected by invisible bonds that transcend space and time. The eternal dance of quantum entanglement continues in every moment, in every corner of existence. In your rest, you become part of this cosmic choreography, adding your own steps to the infinite ballet of being. Sleep now, knowing that you are held by the very fabric of reality itself, connected to all things by threads of quantum light that can never be broken.